Hi, this is Mr. Manley. This is a video on linear programming, which builds on what we know about solving systems of linear inequalities. Probably you've seen systems of linear inequalities word problems, which this looks very similar to. And then there's one more added element that we are going to build on to solve this special type of problem, this linear programming problem. So you might take a moment to read through the problem. And if you've done that, you might be able to follow along with me a little better. I've got a type A and a type B in this problem. It's referring to types of bags. So I've got a type A bag and a type B bag. And a farmer is trying to build a mixture from these two bags. I know that the first bag has 9 pounds of oats. So I'm just going to circle that right now, but I'm going to start off working with that. 9 pounds of oats and 2 pounds of oats in type B. And then I also have this information that the farmer wants to combine the two types so that the resulting mixture has at least 62 pounds of oats. So maybe you could see building a inequality from that. 9 pounds of oats from each bag A, 2 pounds from each bag B, and a total of 62 pounds of oats. So I'm going to write that inequality now. Perhaps you have an idea what it would be, but I'm going to get 9 pounds of oats from each bag A. And I'll just call it variable A. And I'm going to get 2 pounds of oats from each bag B. And what did I need? I need at least 62 pounds. So that sum of oats that I'm getting has to be greater than or equal to 62. Likewise, each type of bag has corn. 1 pound of corn in bag A and 5 pounds for each bag B. And I need at least 26 pounds. So hopefully that's pretty easy for you to get the inequality, the second inequality here, in terms of what we need as far as corn from these two bags. I'm going to have A, that's 1A, plus 5 pounds of corn for each B, and that needs to be greater than or equal to 26. Furthermore, there's some other constraints here, and that's actually what I'm building. Maybe in the past, you would call it a system of inequalities. In this context of linear programming, I'm going to call these the constraints. So I've got 2 constraints, and I have some more information here. The store only has 16 bags of A and only 13 bags of B. So this is producing some more inequalities where I know that A, which is the number of bags of A that I'm using, is no more than 16. So it has to be less than or equal to 16. And B, I think you should see now, is less than or equal to 13. So we have this system of inequalities, your constraints, 4 of them, and we are actually going to graph this just like we would in a similar word problem that is not linear programming. We'll get to the linear programming aspect of this in a few minutes here, but I'm just going to take these and see if I can carry these forward to another page here. I'm having trouble doing that. Try that again. And there they are. And we'll give ourselves some graph paper, an XY axis, and then we'll graph the system. Something that I like to do on this problem before I am graphing the system is to go ahead and think about what type of scale I want to use. And to think about what type of scale I want to use, I want to look at what the X and Y intercepts are. Or since I'm using A and B, this will be the A and the B intercepts. So I'll give myself a little XY table, or AB table as it were, down here. Actually, it might be better to do it right next to the inequalities. So let me do it up here. And then I may be erasing it. We've got A and B. I'm going to number these. 1, 2, 3, 4. Because things can get quite messy here if we're not careful. And then I'm going to take a look at the first one here. And when A is 0, then I would have B is 31. And when B is 0, A would be 62 over 9, which is approximately 7. And then for the second one, when A is 0, I would have B is 26 over 5, which is approximately 5. And when B is 0, A is 26. And then I'm just going to pay attention that I've got this A at 16 over here and this B at 13. So looking on my A values are 7, 26, and this 16. So if I set myself up with a scale here, I think it might make sense to go 5, right? 5, 10, 15, 20, 25, 30 should cover us. And then on the B scale, I've got 31, 5, and 13. So I might want to go more on that scale. Maybe if I go 10. All right, let's try and graph what we've got here. I've got 0, 31, something like this. And I've got 7, 0, something like this. Now, if I were working with pencil and paper, I definitely want to have a straight edge at this point. Very important to try and get these edges as accurately as possible. So with this, I'm going to go there. That's, I'm not 100% happy with that. It's a little bit off up here if you look. Like right around in there. It's not too accurate. I mean, I'm definitely up above 31 on the B axis there, but it's the best I can do with this screen that I'm working with. Then when A is 0, for the second one, I want to talk about the shading too, and I want to number this. So I've got 1 here that I graphed, and it's, if I look at 0, 0, for instance, I would have 0 is greater than or equal to 62 using the first inequality. That's not true, so I would shade away from the origin. So let's do that. And just show with a couple of arrows here. Don't want to overdo it because this is going to get messy enough as it is. Then on the second one, I've got 0, 5. And 26, 0. Somewhere out here. And let's see if we can get a nice straight line through there. Not too bad. That looks pretty good. Okay. We'll number that 2. And again, if I take 0, 0, I would have 0 greater than or equal to 26. Not true. So shade away from the origin on this one. So I'm up here. So I'm clearly, at this point, I'm in the first quadrant, right? With a little bit of angle there as well. Let's take 3 and 4. A is less than or equal to 16. So that's going to be, let me just try and see how straight I can make this line here, this vertical line. I think I can do a pretty good job. And that's number 3. A is less than, so the arrow's over here. So right now, if I stopped, I've got one more to do, right? But if I stop, you can see that I'm right in here, right? That's where my solution is. But I'm going to go one more. The B is less than 13. And it'll come in something like this, right? So my solution set is in here. Because that was B was less than, so I was below number 4 there, which I should number as well. Number 4. And there we would stop if we were doing a word problem from linear inequality systems. But here, with linear programming, we're going to take another step. So first of all, before I take the other step, I want to find these 4 points. These are the corner points. And this might get a little bit tricky because of the space that I have to work with, but so I may go ahead and find a corner point and then erase, and then find another corner point, erase, etc. I'm going to label them too. So I'm going to call this one down here A. Well, maybe I shouldn't call it A. I'll call it Roman numeral 1, Roman numeral 2, 3, and 4. And let me try and keep track of them down here. I think I have some space where it might make sense to keep track of them. So for instance, can you tell just by looking that 3 has an A coordinate of 16 and a B coordinate of 13? And can you tell that number 2, so I'll start off with number 2 here. Number 2 has a B coordinate of 13. Can you see that? That if I was looking here at 2, I was looking here, that this line, this horizontal line, is crossing where those two lines intersect. And I know that horizontal line is number 4, which number 4 is 13. That's where the edge is at. It's at 13. So I've got the B coordinate for number 2 there. And I can also see that edge 1 is passing through there. Passing through point 2. So I've got edge 1 passing through, and I know the B coordinate is 13. So can you follow what I can do here? That I can say, all right, to find A, I know 9A plus 2 times 13 is equal to 62. Of course, we're just going to say equal because we're just looking at the edge. The equal sign tells us where the edge of the region is. And then I can solve this. So that might take me a moment here to solve this, that I've got 62 minus 26 divided by 9. And that's 4. So I get A is equal to 4 when I solve that equation for A. So this is a 4 here. All right? So that gives me corner point 2 at 413. And then we'll go down to corner point 4. It's similar in method to what I did for corner point 2. So if I look down here at 4, I know that this vertical line is passing through it. And I know the vertical line is coming from number 3, which is 16. So I've got the A coordinate for 4. The A coordinate is 16. So I need the B coordinate. I can also see that edge 2 is passing through point 4. So edge 2 is going to be this A. I'll just write it all out here. A plus 5B is equal to 26. And then we determined this A, right? We determined here that A is 16. So I got A is 16. I'll go ahead and do that substitution. We got A is 16. And then let's solve for B. 26 minus 16 divided by 5. We get 2. So here I'm getting B is 2. So this point 4, this corner point 4 is 16, 2. All right, then lastly, I need to solve a system of equations for the place where the edge 1 and 2 intersect at position 1 there, Roman numeral 1. That's edge 1 and edge 2. So I'm just going to take this 9a. Let me just put it out here, 1. All right, and then that's 9a plus 2b is equal to 62. And I'm going to multiply the second inequality, which I'm going to just take the equation part of it and multiply by 9. 9 plus 45, and that's equal to 9 times 26, which is 234. And I'll subtract. So the a's will zero out, and we will have negative 43b equal to 234 minus 62, negative 172. And I'm betting that's going to, what's that going to come out to? Is that going to be convenient? 172 divided by 43. Yeah, that's 4. So I get b equals 4. And we'll back substitute that into one of these equations up here to solve for b. To solve for a. So that'll be 62 minus 8. So stop and make sure you understand that statement that I'm doing. I'm working in the first equation here, and I've plugged in a 4 for b. So I'll have 62 minus 8, which is 54, and divided by 9 is 6. So that's giving me A. A is equal to 6. Okay, so I've got 6 and 4 for that Roman numeral 1. Let me give myself some more space. And did not give myself space down there. Let me get my space there. And, oh geez, I forget now. What was it? It was 6. and 4. There it is. You know how I forgot what it was, but I looked at the graph and the graph told me. So that's a good demonstration of why an accurate graph is helpful. Okay, now we have to go back to the statement in the original problem here, because what I want to do is I want to try and figure out how can I minimize the farmer's cost. So what I have so far, the farmer, this blue region here, those are all the combinations of bags of A and B that the farmer can do. So like the farmer can't go out here and do 5, 10, 15, 20, 30 bags of A and 10, 20, 30 bags of B. He doesn't have that many bags. And I don't want to do too few bags because I want to have enough corn and oats. But the question is, of all these possibilities in the blue region, which one will minimize cost? And what I want to tell you that a main principle of linear programming, which is what we're doing here, is that when you're trying to minimize or maximize a problem like this, the minimum or the maximum will take place at one of the corner points. So that's one thing. That's why we have the corner points, because I know the minimum or maximum will occur at one of those points. But before we figure that out, what we need is something called an objective function. And that usually, at least in terms of a mathematics class, that is usually a function that involves money. Probably trying to minimize money or maximize money. So our objective function here is based upon this sentence here. How much money is it costing the farmer? $5 for each bag A and $1 for each bag B. And that is, I'll say C for cost. And that's probably a pretty typical that you're going to be looking at the cost. And you want to minimize cost. If you're looking at cost, maybe you're looking at the revenue or the income. Maybe use R for revenue. Might depend upon the wording of the problem, and then I might want to look at, all right, I want to maximize revenue. I want to make as much money as possible, or I want to spend as much money as possible. All right, now we're going to take that equation, this objective function, and let's carry that forward to the next page. And we're going to evaluate the objective function for each of the corner points. So at corner point 1, I just plug in those values. 6 for A, 4 for B, and I get 34. Corner point 2, I plug in 4 for A, 13 for B, and I get that. That's how much it would cost me. Corner point 4, I plug in 16 for A, 2 for B, 82. And corner point 3, well, you know what? I can tell corner point B is going to be a lot more money. 5 times 16 plus 13. So that's going to be 93. I'll just kind of do that one pretty quickly here. All right, Let's just go back and look at our question again. The question is, how many bags of each type should the farmer buy to minimize cost? So I can see the minimum cost here, right? The minimum cost is here at 33. 5 times 4 is 20, plus 13 is 33. Pretty close for 1. If I used 1, 5 times 6 is 30, plus 4 is 34, but minimum cost is 33, and that's going to be 4 of bag A and 13 of bag B. So that's a big problem, right? There's a lot to keep track of. And when you're doing this in written form, it is really helpful if you follow some of the formatting methods that I've used here. Numbering your inequalities, using a straight edge, numbering your corner points, clearly labeling your objective function. And this will not only help you keep track of what you're doing, and it will help the reader, whoever's looking at your work, be able to follow what you're doing. And that's linear programming.